All right, so welcome to Dropbox and this talk on Pyston. Clicker. So yeah, this is a talk that's going to go over sort of what Pyston is, a little details about the challenges we've been facing, and what we've done to overcome them, and where we're currently at. So just as an overview, sort of what is Pyston? Pyston is a high-performance Python JIT that we've written in C++. So its goal is to run Python code faster. And one of the main techniques that we use to do this is on the fly, we will generate assembly code, which is where the JIT part of this comes from. Some other facts about the project: we're targeting Python 2.7, which is in some circles pretty controversial. You can go complain about it on Reddit if you would like. The project is open source. We started it in 2013 and open sourced it in 2014. And currently the team consists of 2 full-time members and a number of part-time and open source contributors. So the full-time members are, we've got Marius, who's sitting up here, and then myself. And then we have a number of open source contributors that I wanted to mention as well. So where we're currently at, so we just, in case you didn't see it, we had a big release. Well, we had a release last week where we announced a number of big features. One was that we now have 25% better performance than CPython. And we've also made a lot of strides on our compatibility front. So it's easy to run certain restricted subsets of Python very, very quickly. But the challenge is running all of Python and still having good performance. So we've been able to ramp up both of those dimensions. And so some big milestones we hit is that we can run most of Django, I think all of Django, a lot of the Dropbox server, and some NumPy as well. And in terms of just where we're at in the life cycle of this, is the next big thing that we want to do is actually get running on Dropbox, or have Dropbox running on Pyston. So as I was saying, this talk kind of goes over, what is Pyston? Why did we decide to do it? Because there's a lot of other Python performance projects out there. And then going over a couple of the main dimensions that we've been putting work into this project, which is usually falls down into compatibility and performance. So there's definitely a lot of people who so why Pyston? So there's this conception that Python is just an I/O bound language, and that the performance of running it is not that important. You run a little bit of code, and then you're immediately waiting on the network. And maybe that's true, but certainly at Dropbox's scale, we just have a lot of machines that are just running Python code. And those machines mean we spend a lot of money running Python code. And this is true for other companies as well. I know that YouTube has a lot of Python servers. I think Pinterest runs on Python. There are definitely people who run a lot of application code through Python. So there is an incentive to run it faster to reduce your server count, and also improve your response times to the user. And as I was saying, there is a lot of work that's gone into the Python performance problem. That it's a very common language that people like, and the performance is something that people are often not very happy about. And so why did we decide to enter this somewhat crowded area? So just as a quick recap, the landscape looks a little bit like this, where CPython is the name of the main Python implementation. So often when people say Python, they mean this particular implementation of it. And that's kind of the baseline. I'm going to be referring to CPython a lot in this talk. And then if you write your Python app and then you see that you're not getting the performance you want, you have quite a few options for how to go about it. You can write some of your you can translate your Python code into a C extension, which gets loaded into the Python interpreter, and that can speed up your code a lot. But that's pretty tricky to do. So there are a couple projects out there that try to help you do that in various ways. There's Cython, and Numba kind of also falls into that category. And those have mixed results, but they can do really well if you're willing to annotate your code with all of the types that exist in your system. There's also PyPy, which is something that people often think of when it comes to Python performance. And I'll talk a bit more about PyPy and how I think we're different than them. And then another big option, which isn't really in the Python landscape, but you always have the option of rewriting all your code into a faster language. So there are quite a few options that you have out there, but all of these require a lot of work per line of code that you have, or that you want to make fast. That they're not sort of drop-in replacements that just all of a sudden all of your Python code is faster. You can selectively target some of your code, make it very fast, but with a very large code base that can be very time-consuming and might not be feasible. So we wanted to do something where we could take Dropbox's large Python code base and require very few modifications to it and get better performance across the board. And so that's where we kind of see ourselves fitting in, that we don't think that there's a good solution out there for people that have large code bases and don't have the time, or it just doesn't make sense to spend a lot of time going through every single line of code to try to make it faster. There are a lot of people who have, a very small Python program and they want to make that super fast, and that's not quite what we're targeting, and instead we're going after this workload. And as a part of this, as I was mentioning, there is this ability to write C extensions for your Python code. You can either do this for performance or to interoperate with existing C libraries. So our wanting to have very few modifications, that does imply that we need to have very good C API support, because otherwise we would have to make a lot of modifications to all of our C libraries. Oops, sorry, wrong direction. Cool, so that's kind of what Pyston is, why we decided to do it, where we see ourselves providing value in this landscape. And so the first one is, as I said, we really want Pyston to be as drop-in as possible. That if you need to do a whole bunch of modifications to your program, then you start getting to this territory where you have to start rewriting the entire application in another language that's going to be way faster. So we really want to provide really good support for CPython, for code that the behavior that CPython, the main interpreter, gives you. So there's a number of things that, especially if you're familiar with Python, are going to be pretty big challenges in this. One is that Python did not start as a formal specification from which interpreters or other implementations were written. It started off as a single runtime, and people wrote code to that. And people documented how this runtime works, but it's very far from there being a formal spec. And interestingly enough, there's also stuff that is explicitly documented as not being part of the actual semantics of Python. And those are some of the most popular features because they're extremely useful, and that's why they were added. So we need to support those. There's a lot of stuff that needs to get supported. And that's kind of related to the third point as well, that there is a lot of stuff in Python, and it just wasn't added because someone thought it would be fun to implement. It was because someone found use from that feature and is using it out there. And we want to run a lot of code without modifications, and that means we need to support all those features. The other challenge that we knew about coming into this is that the C API for writing C extensions is very large and very cumbersome. It's very difficult to support, and this has been a stopping point for a lot of other implementations. So we started at a pretty early point to really focus on building ourselves in a way that we could support that. So luckily, we kind of had these in our mind when we started, but there are also a number of things that we learned along the way that we were not quite quite as prepared for. One was programs love to inspect themselves in Python. And they love to inspect lots and lots of details about how they are getting run, where they're getting run from, when certain things happen, when the implementation decides to do certain things. So we have to be pretty careful about keeping that the same. Another thing that was tricky is that we were hoping to put off a lot of this work for a long time, but it turns out that a lot of core parts of the Python ecosystem are actually some of the most used the most of these features. And another thing that we found is that there's a lot of historical stuff in the Python interpreter. If you're familiar with the Python ecosystem, you know that they tried to get rid of a lot in the Python 3 transition. And I thought we could maybe try to sweep some of that under the rug, but there's a reason that they never changed it. It's because it does break code to do that. And another thing, which is not a huge deal, but it's just kind of funny, is that people do kind of now allow for multiple implementations in Python. They do know that they can get run in under multiple different implementations, but they just assume that it's just CPython and PyPy. So we actually lie in a bunch of places and say that we're PyPy, because like otherwise people think we're CPython, and then that's worse. So anyway, so the way we've kind of dealt with this, one of the ways we dealt with this is we've integrated a lot of CPython code. So the C API gets a bad rap because it's so large, and one of the reasons it's so large is it's actually CPython's internal API. And they just export the internal API and anyone can use it. So that's one of the things that makes it really hard to use. But on the plus side, once you support that API, you support all of CPython's internal code as well. So now, if there's some really tricky function that it has crazy corner cases and who knows why it works that way and how to make it work in our system, we can literally just take that code, copy it into CPython, copy it from CPython into Pyston, and then it will work. And so as we've gone on, we started as a from scratch implementation where we just started bare repository, started writing code. But now we're actually at the point that I think the vast majority of the code in Pyston is originally from CPython. So that means that we're actually very close to the CPython code base, and that's been way by far the most effective way for us to support all these crazy semantics that Python has under the hood. All right, sorry about that. Yeah, this is, my laptop's on Linux, and so that's basically all you need to know for why that happened. Okay, so as a result, this has actually been a huge, huge benefit to us, something that I think has been a really good choice for us. Because now, we no longer have to worry, does our set implementation do something differently than CPython's? And are there going to be weird corner cases that we're not going to know about that we're going to run into? It's sort of, when we copy CPython code, we get to be correct by default, which is a really, really nice place to be because you don't usually get to have that. And as a result, just some of the things we support a lot of common libraries, a lot of them taken from the Dropbox servers. But Django, SQL Alchemy, LXML, Babel, Cheetah, can't even name them all. And we actually run their test suites as part of our testing process. And so we are pretty sure we have pretty good support for them. We run a bunch of the Dropbox server. It's hard to measure exactly how much because once you hit one bug, you can't see how many others you might have hit or not. But we can render a number of pages, as many as I kind of tried. And we do have some NumPy support. We don't use NumPy that much at Dropbox, so we didn't invest that much in this. But we had one of our interns spend 2 days on it, and he was able to get a bunch of NumPy examples working. So I think that's pretty promising on the NumPy front. But we're pretty happy with the compatibility that we've been able to reach on all of this. One thing I didn't mention is that this experimentation of starting from scratch and slowly moving to CPython has meant that we got to experiment with a lot of different aspects. There are a lot of things that CPython is very careful to support, and we found that no one actually uses. And there are a lot of things that they say that aren't that important and actually are, and we had to backtrack on. So there are pros and cons, but I think we have a very good sense now of where we can really drive ourselves forward and make things better, and what things are just really core to the language. And this isn't quite related, but something a lot of people ask about is the GIL. It's kind of, no one likes it in Python. It's how Python handles concurrency. And I personally don't like it. Looked into getting rid of it, but just the fact of the matter is it's part of Python. And our goal is to produce a extremely highly compatible version of Python. And to do that, you have to add a GIL. So we did. And so that's what we have. And maybe once Python 4 comes out, there won't be a GIL, and then we'll migrate to that and then not have a GIL. Cool, so now moving from compatibility to the performance section. This first part is about what makes Python hard. That there's a lot of different reasons that a language might be hard or not to implement. There's a lot of other languages that have had really good implementations come out. And so where does Python kind of live in all of that? And how much can we appropriate from these other techniques? So to begin with, I want to start with, why is it hard to beat CPython? It's like, they're an interpreter. Interpreters are supposed to be the lowest class citizen of implementation techniques. Like, why isn't it easy to beat them? And if you look at the research literature, it's trivial. Everyone can beat it by 30%, and there's all these papers saying they do that. But in reality, CPython is really well optimized to do what it does. Like, if you can't avoid the dynamicism of Python, then CPython has the right implementation of handling the actual dynamic case. And even sort of stronger than that is that people write their code knowing it's going to get run on CPython, and they optimize it to get run on CPython. So we need to not only try to run normal idioms quickly, but we need to support code that was optimized specifically for CPython. Another thing that makes beating an interpreter hard is there's a lot of, especially in Python, there are a lot of things where there are very short sections that are extremely hot. So like looking up an attribute on an object gets called all the time. And it's an extremely short function that does that. And so if you add anything to that, you're going to get a slowdown. So even if you add a check, like should we do the more expensive thing or should we fall back to the normal thing, that's going to make you slower than CPython, which doesn't do that check. So it's not a huge slowdown, but you will see that just tracking extra information around through your runtime does pay a cost because CPython is so tightly optimized. So going forward, trying to do better, the common thing that people say is, oh, Python is hard to run because it doesn't have static types. You have your variables, you don't have to say what they are. They can even change through the course of a function. So the compiler would not know how to handle what that object is. But sort of the point I'm trying to make is that actually if you did have that, it would still be very hard to run Python quickly. I don't think this is quite the right reason why Python is hard. So here's an example of something that's taken from Django, where it kind of hopefully illustrates that a little bit. This is during their template rendering phase, where they take a string from the template, they run it through a regular expression, they take the output of the regular expression, and they look that up as an attribute name on this settings object. So you can say, by the way, I'm going to compile this, I'm going to render this template, and I decided that some setting is now different. And this is how they handle that. So we can do a pretty good job. We can tell that var name is now Unicode in this particular case. But settings is this thing called lazy settings. And it's called lazy settings because it doesn't actually load the settings until you access it. And so that means that it defines all these dynamic hooks for how to determine when to actually load the real settings, how to forward calls to the real settings, and so on. So even if we know that what settings is, and we know what var name is, and none, obviously, we know what it is, it doesn't really make executing that get-attr call that much easier, because it's still going to have to do a bunch of dynamic stuff. And there's a bunch of other examples in this. I won't get into them too much. But there's a bunch of cases where even once you know the types, you know the function you're calling, you know the argument types, there's still going to be dynamic behavior in there that just the types themselves don't give you. So the way I kind of say this is understanding the types in your program is only the first level of dynamic behavior, because the functions that themselves actually exhibit dynamic behavior themselves. Another thing that I think is a little bit of a misconception about Python is that Python is dominated by interpreter overhead. So this is looking at the generated bytecode, dispatching based off of the opcodes that you see, and then loading things from memory instead of registers, and then doing your operation and putting them back into memory. And at this point, with the optimizations that have gone into CPython and modern processors, this is actually maybe 10% of the runtime. So it's significant, but it's not very much. It's if you just get rid of that, you're not going to improve things that much. So what are we going to try to get rid of when we build a JIT and spend all this time and effort on building one? And my thought process on this is that we need the JIT to not just understand the Python code. The JIT really has to understand the runtime. This is all the C code that gets built into the Python interpreter that determines how the get-attr call works, or the len call works, or how constructors get called. So we really need a technique that can understand that and not just Python code itself. So that's kind of my thoughts on what makes Python hard, and here's what we do to try to address that. This is a brief overview of our pipeline. It's mostly pretty standard. We take Python code, we parse it, we turn it into a bytecode, and then we feed it off to an interpreter. So far, it's pretty much just like CPython does. As it spends a lot of time in the interpreter, we bump it out to this baseline JIT tier, which is not super smart, but it is much better than the interpreter. And then once it spends a lot of time in the baseline JIT tier, we bump it out to the LLVM JIT tier. And LLVM, at least in theory, can do much more hardcore optimizations on this code. The one important thing, though, is that we also have this extra piece of infrastructure that we have a tracing-JIT inside. And this tracing-JIT can sit between our baseline JIT and LLVM JIT tiers and control how they interact with the runtime. And that tracing JIT is actually where we get most of our performance speedups. So our tracing JIT is, so I'm going to talk mostly about the tracing JIT. The other ones are what we talked about a lot originally, but we've actually, as I said, been getting most of our benefits from tracing, so I'm going to talk about that. Our tracing JIT is pretty low tech. I mean, it's still a JIT, but compared to other tracing JITs out there, it is not very fancy at all. It operates on a single operation, such like a single function call at a time. So it doesn't look at large regions of your program. It's just a single function call. And it stops looking at that function call once you reach more Python code. So it doesn't do any inlining. And the last thing is that it requires manual tracing annotations in our runtime in order to trace the code. So compared to a lot of other things, this seems pretty low tech, but we've actually been getting a lot of benefit out of it. The manual annotations are one thing that are probably the most controversial because they do require some sophistication to write. But one of the reasons that they're difficult to write is because we can write them very fine-tuned in a very fine-tuned way. We can write exactly the annotations we want. We can get it to produce exactly the trace code we want because we're all doing it manually. So it was easy to set up. It always works for any case, and it can get us exactly the code out that we want at the end. We want to find some ways to make it easier to write, but so far it's been a pretty good trade-off. So here's a quick example of how the tracing-JIT works. Here's a quick Python snippet where we're just calling a simple Python function. The tracing-JIT is going to have just a built-in set of rules that when you call a function, you verify that the function is the same thing that you thought you would be calling since you saw it last time, and then you call it. And then it breaks these steps down into sub-steps. And in this case, that means checking to make sure that the foo name refers to the same variable. And in Python, there's this thing where you can actually take an existing function object and change the way that that function object works. So we need to be protective against that as well. Then we need to call it. We have a fast way of calling into Python functions. We use the same way that C calls into functions, which is a bit faster than the way that CPython calls into functions. And so yeah, this is the simplest case of tracing, but I just wanted to use it as an example of how it works, and also to show a little bit about what are some of the benefits that we can get out of this, even in the simple cases. So we can have very fast ways of doing all of these steps that are faster. So we can do each of these steps faster than CPython can. We have fast ways of checking to make sure the variable is still the same thing. The mutations are rare, so we actually use a slightly different technique, which I'm not going to get into, but that we can actually skip that step there. And as I mentioned, when we actually call the functions, we have a faster way of doing that. So here's a slightly more complicated example. We have an object of some custom type, and then we try to get the length of it. So the tracing-JIT goes in, has the same strategy. It says, check to make sure the function is the same thing that we thought it was, and then call it. But in this case, len, which is a very standard built-in function in Python, which gives you the size of an object, is actually important enough that len knows how to trace itself. So len says, okay, well, I have an argument. It's of some kind of unknown type. It's a user-defined type. And so what I'm going to do is I'm going to call arg.under_len. This is the protocol for how len works. And then the tracing-JIT says, okay, I know how to call functions. Here's what we do. We check to make sure it's the same, and then we call it. And then yada, yada. It keeps on expanding that, and it'll trace through all the behavior. And under_len could be not just a user-defined function. It could be something defined in C code, so then we have a special way of handling that. So this is kind of an overview of how our tracing-JIT ends up producing very efficient code for executing these operations if they happen in the same way as they did the first time. So that's kind of an explanation of how the tracing-JIT worked, but it doesn't mean that the tracing-JIT is the only way to achieve that effect. We actually started off with a more traditional method at a time JIT, where it's more of a top-down approach. You say, okay, we see that this is a len function being called, and then we expand into that, and then you recurse on all of that. So we started with that kind of approach, and we ran into issues pretty quickly, mostly related to the multiple levels of dynamicism that I was talking about. And we kept on finding that the best way to solve those were to increasingly rely on our tracing-JIT. So one issue is that a very common thing in JITs is that you want to understand the behavior of your program to understand what the expected case is. Because you're not focused on running all cases faster, you want to find out what the expected case is and specialize on that. And so if you're only dealing with types, that's kind of straightforward. You record the types, and then you know what the types are likely to be. But with some examples like this, we need to know there's a bunch of steps that happened here, and there's a complicated path that it took through the runtime. So we need some way of representing that in a pretty rich way that can represent all of these different cases. The tracing-JIT also lets us do some things like when we trace through something, it can decide that, hey, I don't think it's going to be profitable to specialize any farther into this function. It has a bunch of heuristics for determining that. And it can say, you know what, rather than try to trace into this function, I'm just going to emit a call to the function. And so we get a lot of control from that. And this will come up in the comparison against PyPy. And the last point, which is, I think, pretty important, is more of an engineering trade-off. That with a method JIT, we could have put all this information into the thing that analyzes Python code. So it's looking at the Python code, and it says, this is len, and I know how len works, and I'm going to do this. But instead, with the tracing JIT, what we get to do is we say, in the len function, it says, oh, I'm being called in a tracing environment, and I know how to trace myself out. So just from a software engineering perspective, it lets us keep those sets of code together, and it makes it much easier to verify that the tracing annotations actually do the exact same thing that the function annotations, or that the non-traced version does. Because we have a lot of tracing annotations at this time, and it would get very unwieldy to manually verify that. Cool, so yeah, as I promised, I wanted to compare a little bit against PyPy, because they use a tracing JIT as well, a much fancier tracing JIT than we do. And so I wanted to talk a little bit about why both where we see advantages against PyPy, and also why we think we're more suitable and for the Dropbox-like environment. So PyPy has a couple things that we think are missing. One is fairly well known, is that they have very poor C extension support. And they try to say that that's not a big deal. I think it's a big deal. I'm biased. But just doing a quick count, we have roughly 80,000 lines of extension code at Dropbox. Not that we wrote, but that we load into our servers. It's much less than the amount of Python code we have, but it's still a lot of code. But this is kind of something that they already get bashed for a lot, so I won't go into that too much. The thing that I think is more important is they seem to have trouble with performance scalability. And what I mean by that is they do amazingly well on micro benchmarks and small programs. But as you scale to larger and larger programs, their performance gets worse compared to PyPy. PyPy's performance gets worse compared to CPython. And it's actually not unusual at all that PyPy's performance ends up being worse than CPython. So I have some more slides after this one where I'll go into that. And one thing that I just wanted to throw in too is that obviously we started behind PyPy because we started quite a bit later than them. And just for fun, we measure, for every milestone of ours, we check to see what milestone of theirs was the same performance as the one we just currently hit. And so, the place we're currently at is in their past, but we measure how fast we're catching up to them. And so the unit we use for that is the number of years of their work we catch up every month. So we're pretty happy with that, I think it took us 3 or 4 months to catch up about 4 years of their work. So we're coming up on them pretty fast. And pretty soon, hopefully, the next presentation you see, it'll be where we're pretty far ahead of them. I promise. Yeah, so sorry, this is going back to performance scalability, where as you scale the programs, it's not clear, I don't think anyone has a good sense of why this happens, including the PyPy developers. But as you scale up the programs that you run PyPy on, the performance gets worse. And someone, I don't know if he's here, actually tried running the Dropbox code base on PyPy, and the performance measurements weren't super rigorous, but it looks like they were roughly on par, and there's no clear benefit, no clear winner either way. Another stat that I like to give is if you just look at our benchmark suites. They have their benchmark suite, and we have our benchmark suite. And their benchmark suite, the average benchmark size is 36 lines of code. So they're optimizing for running things that are 36 lines of code long. And whereas ours isn't, we're still working on getting bigger benchmarks, but we're about 20 times larger than they are in terms of the benchmarks we test on.
Are there any outliers in your benchmark base, or is it all around? So it's not like you have one benchmark that's a kind of outlier.
Yeah, this is the geometric mean of them. So it ends up, the outliers end up kind of balancing out. Ours are usually in the 500 to 1500 range. Theirs, I think, are usually lower than 36, and they have a bunch that are a couple hundred. Yeah, I mean, I like to give them crap about this, but it's just one thing that I think shows you kind of a different focus in the two projects. I wanted to give a more technical example of this as well. So I wrote a simple benchmark where it's just a very simple attribute lookup benchmark. I don't know if this is what is causing these kinds of regressions as they scale up, but I think it certainly demonstrates the kind of behavior that you see across a number of different types of benchmarks, but I'm just showing one right now. So this is a simple benchmark where basically on the x-axis, you have increasing problem difficulty. So we are going to look up a single attribute name on a bunch of different objects, and the x-axis shows how many different types those objects have. So on the left, it's just a single type. We just get the attribute all the time. And on the right, there's 512 different types. So there's a logarithmic x-axis here. This blue line is CPython. So they have a pretty consistent behavior as you increase the problem difficulty. It does get a little bit worse because they have internal caching and stuff, but it's still pretty consistent. This red line is Pyston, where you can see that for one type, we do about twice as fast. For two types, I guess, I don't know, 20, 30% faster. And then beyond that, we're usually within, I can't tell, 5, 10% of them. So there is that overhead that I mentioned. And we're pretty happy with this. For common stuff, we're going to do better, and for everything else, we're going to do roughly the same. PyPy's graph looks very different. So first of all, that's the start of their graph for the low numbers. And it looks great. That very first data point is 8 times faster than CPython. So if you're running that, if that's your workload, you're going to get their promised 8 times speed up. But then if you keep on expanding their graph out to the right, you get this. So it's 38 times slower when you get to 512 types. And there's some debate about exactly how many times do you hit those kinds of situations, and I don't have numbers on that on me. Those do definitely come up. You can definitely imagine that in a ORM example, you have one type per database table in production, and you can easily have way more than this database tables in production. And you don't need to spend that much time in a section of code that is 38 times slower for it to really add up and start to regress your performance. Yeah.
Do you have a guess for why the behavior looks like this?
I think they try to trace. They do not stop trying to trace. So they will keep their tracing machinery activated continuously, and that's roughly the overhead of it. So it does kind of flatten out if you extend the graph farther. Their overhead doesn't keep on increasing exponentially. So yeah, I think it's their tracing overhead. But yeah, I don't think they know, so I'm not going to probably know either. And yeah, this is just one dimension of problem difficulty that I picked. I also picked a couple other ones that weren't quite as dramatic, but showed the same behavior. So like control flow difficulty. If you have lots of different control flow paths through your program, they will steadily do worse and worse until they're worse than CPython. So yeah.
How much memory does your tracer take?
Oh, our tracer is very small, and it does quite well on memory. I think overall our memory usage is not where we want it to be, but at least for the tracer itself, it's quite good. And also because we trace much smaller units, it's much more likely that our trace is going to hit and not get invalidated. And also we don't keep it's not our main, for various reasons, it's pretty low overhead. It's definitely expensive enough that we can't keep it activated all the time. And we do have a bunch of heuristics for determining when to turn it on and when we need to keep it off. But it seems to be much lower overhead. Cool. So yeah, anyway, that's my bit about PyPy. Pretty positive about our ability to take them on. They definitely seem to be kind of letting us catch up a lot. Cool. The final section of this talk is about sort of, where we're going and our roadmap. So as I mentioned a little bit earlier, the main thing that we're working on now, the thing that we're focusing on, is really getting ready for being used in Dropbox production. That, as I said, we support most of Dropbox Server. We only had to disable a couple very rarely used features, but we need to hit that last 1%, and that last 1% is always the hardest. So there's a couple things like, we have the ability to inspect stack frames. This is a very common thing in Python. But actually what you can do is you can inspect a frame that exited any amount of time ago if you saved the right amount of data. So we don't have that ability and we need to build it. And I think it's almost done, right? There's a couple other small things like signals support for Unix signals. And we use a GC, and it might actually, I think we're starting to find that the compatibility break from that might be too much to handle. And it's also a performance, it's been tough on performance. So these are sort of compatibility things that we're working on. Those are the main focus at the moment. And then we have a bunch of performance work that we're always doing in the background, well, right now it's in the background until we can get launched. But we have a bunch of exciting things. So as I said, our tracing-JIT works on a single bytecode at a time. So for that bytecode, it can produce really, really good code. But then the next bytecode, it's not going to remember anything it had done in the previous bytecode. So it does a lot of duplicate work. It doesn't really know the relationship between things, how one bytecode might feed into another one, and you could have savings through that. So what we want to do is we want to integrate our tracing-JIT with our LLVM-JIT. And I think that's going to get us to like the next level of performance on these things. There's a couple other projects that I just wanted to throw up there. Our interpreter tier is not as fast as it could be. We currently don't do any function inlining. And so these are the kinds of things that we want to start working on. Cool, and as I mentioned in the beginning, this is an open source project. We are definitely always interested in taking on new contributors. We have a pretty long list of starter projects and just projects in general. I didn't want to swamp the slides with them, but I'm definitely happy to talk about them. We have a Gitter chat channel, which I'll give out. It's like Slack or IRC. You just jump on and we're on and you can chat with us. And yeah, just come by, say hi, and start hacking. Cool, yeah, and that's it for the presentation. So any questions?
You mentioned on the blog that you guys were from all these different instances. Use that for the next restart if possible, or is that going to be pretty tough?
Yeah, I mean, we do cache from run to run. I don't know, Maris, do you want to chat about that at all? Or? Yeah, I think most of the machines will probably generate the same cached code, but we could warm up on one machine, take the cache, move it to another machine, and then it wouldn't need to warm up its own cache, that kind of thing. I don't know if it would be enough to kind of stitch together in the end and have a complete program or anything like that. But anyways, it's been helpful so far.
Yeah, so the course this is with tracing-JIT. I don't think I yet quite understand what you mean actually by tracing-JIT. I've spent a little bit of time with pipeline and tracing-JIT, and it sounds like it means something else, but I'm not sure yet.
Yeah, I mean, it's not really a conventional tracing-JIT. Basically, we track this information through the runtime, saying, here's, a runtime function will receive not just its arguments, but an abstract representation of its arguments from this trace that we're generating. And so then as it operates on its normal arguments, it's going to do the equivalent operations on these abstract trace level arguments. Sorry?
That's the annotation.
Yeah.
Where it says, hey, by the way, I just looked at this argument.
Yeah. Yeah. So as we go through the runtime, it's going to be incrementally outputting these assembly instructions. And then in the end, we end up with a trace of the behavior that it took through the runtime. And then we can next time just execute that instead. But yeah, so it's a little bit different. It's definitely not what you would build if you set out to build something called a tracing-JIT. Yeah?
So how dependent is Pyston on the LLVM backend? And why was LLVM chosen over some other backend or a custom backend?
Yeah, so maybe I can go back to the architecture slide. So our initial architecture was you take out everything except for the parser and the LLVM-JIT. So I started off parser to LLVM-JIT, and that would interact with our runtime. And I thought that the LLVM-JIT, LLVM can do no wrong, so it's going to be amazing, and it's going to make Python super fast. At this point, we're not getting a huge amount from it. The speed of the baseline JIT tier and the LLVM JIT tier are actually pretty comparable. And that's because their speed is dominated by the tracing JIT. So they both are mostly just ways of providing a framework for the tracing JIT. But yeah, as I said, we hope to be able to stitch multiple traces together and then do some higher level optimizations over that. And so the LLVM JIT is probably going to be a much better fit for that than trying to cram that into our baseline JIT. Cool. Any other questions?
Yeah, so now that you have all this experience, you're thinking about back to kind of, if you wanted to say like build Pyston for Python 3, you could start from scratch. How would anything you'd architect it?
I think I would definitely start directly from their code base and fork it for one. I think it would have been hard to do that and know what to rip out or not, especially because like if you have the code base and you try to rip something out, it's going to touch every single part of it. So it's sort of a very complicated operation to try to do something like that. But yeah, I would probably start directly from their code base and rip out the code execution stuff, and then go from there. Yeah.
I'm just curious about the architecture of your baseline JIT. Is that just a typically flat JIT, or like what style of JIT is it?
Marius, you want to take that? Marius wrote it.
It's very primitive. It always just operates one basic program. It basically just generates calls into external functions, or it also generates these inline caches where we can do our tracing, but it's really simple. It doesn't do any optimizations. But it showed up that because our interpreter is so slow, we have to switch to the baseline JIT pretty soon, and so anytime we spend more in the baseline JIT, it regresses the performance because it's such a often encountered case.
Cool. Any last questions? Okay.
Can you talk about what the challenges would be if you were to decide to support the recent Python threats?
Sorry, support what?
Instead of being Python 2.7, if you were to go to Python 3, whatever, what would the challenges be?
I don't have a good sense of that. The things I have seen, though, are that no one has tried to build an implementation that is both Python 2 and Python 3 compatible, that they always fork their implementation. I mean, practically also we would be building something that wouldn't run Dropbox code, so that would be tough, a tough sell to management. Yeah, I'm not that familiar with all the differences. I know there are some things that are pretty tricky, like the integer type, the combination of the integer types, or I think a lot of things that become Unicode that used to be strings. But yeah, I'm not an expert on it. I guess kind of as an aside, my hope is that we can at some point start experimenting with like adding some small Python 3 features into Pyston as we update the Dropbox code base, and maybe try to figure out some sort of upgrade path. Hopefully a smoother one than a lot of other people seem to have had to go through.
What's the likelihood of any of these techniques being incorporated into the main C Python implementation of this package?
Yeah, that's a good question. I mean, I think personally I would love to see that happen at some point. I think it's definitely really far away. And I would rather optimize for getting to the point that someone might even want that, rather than saying like we're going to restrict ourselves now and try to only do things in a way that are going to be merged later. So I guess that's going back to the giving ourselves freedom to experiment stuff. It's interesting. I think there are definitely things that we've done that I would like to see in CPython. CPython has a very strong priority on portability. So they don't want to take in a lot of things that are definitely faster, but would hurt portability in any way. So I don't know how that plays into it, because a lot of things that we do, one example of this is Python re-implements a lot of the data structures. So they re-implemented regular expressions, they re-implemented long integers, and that's good for portability because they have this implementation. They don't have to worry about being available on that platform. But their implementations are pretty slow. They're like twice as slow as sort of modern implementations that you can get. So yeah, there's definitely areas where we think we can help. But yeah, there's things like that. There's also, we have spent almost no time supporting anything other than x86 64. So we've been very aggressively focused on, Dropbox runs Ubuntu, x86-64. And so we have not made any attempts to really support any other architectures. So I think those kinds of things would be pretty tough for the CPython community to swallow. But I hope that someday, I mean, since we're sticking so close to their code base, I hope someday it doesn't have to live as a completely separate thing.
Talk to Peter about it.
Yeah, he was supposed to be here, but he got sick. But yeah, I haven't talked to him about this specifically because it's like, this is the problem that we're going to deal with after we become super successful. So I'm going to focus on that first. But yeah, hopefully someday this becomes a really big issue because that'll mean something really good for the project. Cool. Anything else? Cool. Well, thanks for coming, everyone. I'll be sticking around, and looks like there's still some drinks and everything. So feel free to mingle and come and chat with me. Okay.